In this video, we will look at active filters. So when we choose a filter, we must decide on what characteristics we want. There's three characteristics we need to think about. It's flatness of attenuation. So if we look at the board plot in the top right of the slide, flatness of attenuation is how flat this part of our plot is. Flatness of phase, which is this part of our board plot, or the steepness of transition. So how quickly it changes between accepting frequencies and rejecting frequencies. So it's this part of our diagram. Usually we can only optimize one of these at the expense of the other two. So we need to decide which is the important aspect that we need to concentrate on. The common types of filter are Butterworth, Chebyshev and elliptic, which focus on the attenuation aspects, and Bessel, which focuses on the phase aspects. So we will not be bothered about the Bessel filter, but in terms of the magnitude attenuation filters, Butterworth, Chebyshev and elliptic, these are the typical responses. So Butterworth is optimized for a flat attenuation, so here and here, but that is at the expense of a relatively shallow transition. The Chebyshev types 1 and 2 have got a steeper transition, so better definition between the acceptance and reject. However, they have got ripple in the attenuation. In terms of the type 1, the ripple is in the pass band, and in type 2, it is in the reject band. The elliptic has got the steepest transition, so excellent between acceptance frequencies and rejection frequencies. However, as you can see, it's got the most ripple in the attenuation of these filters. This is a typical example of an active filter. It's known as a Sallen-Key filter, and we've got our op amp here, and we've got either a resistor or capacitor at these four locations. If we work out the transfer function of this, it comes out to be this term here. So this looks rather complicated, but if you look at the exercises, it takes you through step by step how to work this out. For the case of a low pass filter, what we're going to do is put resistors in at Z1 and Z2, and we're going to put capacitors in at Z3 and Z4. So what we're going to do is put a resistor in here and here, and we're going to put a capacitor in here and here. We can rewrite the transfer function as this, where we've just defined omega nothing squared as this term here, and zeta here as this term. And this is a classic second order system where omega 0 is our resonance frequency and our zeta is our damping term. So if we use MATLAB to plot that up, we're putting some just typical values for resistors and capacitors. We get out our resonance frequency of 3.8 kilohertz, and we get the board plot corresponding to this. So as you can see, it's very similar to our passive filter. Two things to notice: this roll-off is steeper, so the transition is steeper in this case, so it's a better performing filter. And then secondly, our phase change in this case is 180 degrees in total. So the 3 dB cutoff point on here corresponds to a 90-degree phase shift. Now it looks quite complicated to design filters like this compared to our passive case. However, we don't have to, because we do have filter design programs in order to do this for us. So we'll work through an example in a minute, but if you go onto this website, what you do is you get a page something like this, and what you do is you type in, so for this low pass filter, what we're doing is putting in our cutoff frequency. So that's our 3 dB cutoff frequency, so 10 kilohertz. So we want to pass frequencies below 10 kilohertz, and we want to reject frequencies above 40 kilohertz. So it gives us this plot, and then it decides what the best filter is to do that, which in this case it's gone for 4th order Butterworth, and then it tells you what circuit you need to accomplish this. So as you can see, what it's designed is actually a Sallen-Key filter here. So it's just our Sallen-Key filter and another Sallen-Key filter here. And it tells us what components we need to accomplish this. The Sallen-Key is classed as a 2nd order filter because it's got 2 reactive components, namely the capacitors. So one Sallen-Key is a 2nd order filter. Because we've got 2 Sallen-Keys, then that's a 4th order filter. So we've got a 4th order, in this case, Butterworth filter. I would just like to point out also, it's given us some advice here, which is bypass capacitors. So I just want you to ignore that for now, but we'll discuss that a little bit more in tomorrow's video. As an example, we'll try and design a bandpass filter. So we've got a choice of frequency, what we want to center this at, somewhere between 3 and 10 kilohertz. And we'd like to attenuate it greater than minus 40 dB beyond these frequencies. So that's the values we've decided to go for. We'll say we'll center it at 5 kilohertz in this case. So I've decided on that. We'll have a pass band of 1 kilohertz. So the width of this peak at the top is 1 kilohertz, and we're supposed to have attenuation of minus 40 at 10, so be out of the frequency range of interest. So we set minus 40 at 10 kilohertz and beyond. We'll push that a little bit harder, so we'll say minus 50. So we'll just ask a little bit more of the filter. So what we'll do is we'll try have a go doing that on the filter design program. So these programs are supplied by electrical component companies. The idea being they're free to use and you get to design your circuit, but then when you come to make it, it recommends their components, so they make their money because you're buying their components. So that's how it works. So what we're doing is we want to design a bandpass filter. So bandpass, we have said we want a center frequency of 5 kilohertz. So we'll type 5 in there. We want a pass band width of 1 kilohertz. We'll put 1 kilohertz in there. So within that range, it's only going to drop minus 3 dB within that 1 kilohertz. We've set a stop band. So anything beyond 10 kilohertz we want to reject, and we've said reject at minus 50 dB attenuation. So we're asking a little bit more than the problem specified, but we'll see if we can get away with that. So if you have these values too stringent, then the software might not be able to design your filter. So you kind of just put any values in here, but these are reasonable values what I've used. So it should be able to achieve that. We've got a choice of the type of filter. So at the minute it's recommending a sixth order Butterworth. We can go for fewer stages. So we can bring it, and that's bringing it into a Chebyshev. And you can see because it's a Chebyshev, we're getting some variation in attenuation in the passband. Or we can go for faster settling. So it's changing it into a Butterworth Bessel. So there's various options what type of filter we want. We'll just go for the Butterworth for now. So it's a 6th order Butterworth we're going to design. So that's what we'd like. There's its suggestion for the circuit. So it's 3 orders. So we've got 3 filters stacked up. So this is not the Sallen key. If you look, it's slightly different, but equivalent. So that's its recommendation. If we go on from there, if we look back at the magnitude plot, we can see the magnitude plot's been changed. It's now got a blue line attached, and that is the error we might get when we design this. And this error comes about because we don't exactly know the resistor values. So when you buy a resistor, you can get different tolerances. So resistors and capacitors, you can get different tolerances. So if we go for a fairly cheap resistor with a 5% tolerance and a fairly cheap capacitor with a 20% tolerance, you can see because we don't exactly know what values we're using, then we might get a variation in the actual filter. We could go for a lot better tolerances on these, and therefore we're a lot more confident what response we're going to get. However, the drawback of that is these components will now cost more because they're better specified. So it's just a question of how much you're willing to spend, what tolerances you can get away with. So we'll go with 1% on the capacitor and 1% on the resistor, and gives us this kind of response. So we're happy with that. You can see it's centered at 5 kilohertz, and it's starting to, once you get above 10 kilohertz, it's actually more than 50 dB attenuation. So it's got rejection at the frequencies we don't want. So we'll just check our circuit again. And there's our final circuit. Again, we've got bypass capacitors in, which I'll mention tomorrow. But that's what we'll want to design. It also gives a bill of materials. So it gives us a shopping list to go out and buy these components. So when we come to wanting filters, then this is by far the easiest approach. Use this software to design them. So for this module, it is important to understand the background behind filters and sort of where the transfer functions come from. But at the end of the day, we'll be designing circuits to use. So we want to design it for a specific job, and therefore get onto the software, get the computer to work out the filter you need and use that. We have been looking at analog filtering. Digital filtering is an alternative. For this, you feed your signal into a computer or microcontroller and then use software to do the filtering process. It is a very powerful technique, but to go into detail, you would have to do a module on this subject. So I've just given a very quick reference for those who would like to know a little bit more about it. However, you should always aim to have the best signal possible going into your microcontroller or computer, so you can maximize the digitization range of your signal. So even if you're using digital filtering, it is still useful to use some analog filtering prior to that to get the best signal possible. So that concludes our discussion on filtering. In the next video, we'll look at some other op-amp circuits that you might find useful.